In this video, we vividly introduce our method with graphical qualitative and quantitative results. Semi-supervised learning holds promise for cost-effective neuron segmentation in electron microscopy volumes. This technique fully leverages extensive unlabeled data to regularize supervised training for robust predictions. However, diverse neuronal patterns and limited annotation budgets may introduce a mismatched distribution between labeled and unlabeled datasets. The mismatch problem may hinder the generalization of semi-supervised models. To bridge the distribution gap, we propose an improved neuron segmentation pipeline by integrating selective labeling and semi-supervised training. You will see the actual distribution transformation induced by data selecting and mixing. Selective labeling seeks to find the most representative subvolumes in the unlabeled volume. Note that each candidate subvolume is composed of patches with spatial constraints. Here we use the AC3-AC4 dataset as a demonstration. To begin with, we conduct unsupervised contrastive learning for the embedding network to obtain low-dimensional and semantic-rich representations for 3D EM patches. We employ UMAP to project patch embeddings into 2D space. Clustering these vectors allows for identifying biologically meaningful distinctions. Based on the embedding network, we design a coverage-based heuristic to identify the valuable subvolumes as labeled data. This algorithm adopts the k-nearest metric to evaluate the semantic coverage of the selected data. In the same embedding space, we visualize the selection process of this method, which achieves significant improvements over random selection in coverage rates. Once labeled data is ready, we perform semi-supervised training for the segmentation network. To promote the mutual transfer of information between labeled and unlabeled data, we innovatively introduce spatial mixing into the neuron segmentation task. We employ axial through masking strategies in spatial mixing to avoid the potential semantic ambiguity caused by anisotropy. This enhancement allows us to build cross-view consistency via intra- and intermixing of labeled and unlabeled datasets. Again, we project patch embeddings extracted by the encoder of the segmentation network. The mixing strategy effectively bridges the distribution gap between datasets, encouraging the segmentation network to learn shared semantics. Next, we present the quantitative results with different annotation budgets. In the semi-supervised setting, the proposed framework, utilizing labeled data selected via CGS and a segmentation network trained by IICNet, demonstrates consistent improvements over other combinations across all annotation budgets. It achieves comparable performance with fully supervised methods, even with only 10% labeled data. In addition, we provide comprehensive visual comparisons of affinities and segmentation results. The proposed method shows significant advantages in maintaining the accurate connectivity of reconstructed structures. All codes and data will be available. If you have any questions, please feel free to contact us.